Hello everyone, Paul Stechik with NEPSI. Welcome to Tech Talk session number 5. We are happy to have you back with us. If you've been with us before, if you're new, thank you for participating and showing up today. So today we are going to be talking about arc flash hazard mitigation as it applies to metal enclosed harmonic filter banks and metal enclosed capacitor banks at the medium voltage level, 2.4 kV through 38 kV. So sitting behind me here on our backdrop, this is new, we have a project that we supplied to Toquepala mine site in Peru. And one thing to always think about when you're specifying metal enclosed systems is to think about arc flash hazard mitigation, because you have a lot of people that will be walking in front of this equipment, and arc flash hazard is something that should be considered. The mines use what's called a zero harm concept, where health, safety, and environment are considered, and this is a critical matter that should always be considered when designing harmonic filters. When you think about arc flash hazard mitigation, two things come to mind from our standpoint. One is the actual hazard to people standing in front, the operating personnel. Okay, the cost of their life, the cost of them being injured, and the litigation cost that follows. The other thing is the actual equipment. When you're supplying equipment into a very critical process facility, LNG plants, mine applications, petrochemical plants, those types of facilities, arc flash hazard mitigation also speaks to the reliability of the equipment. If we have an arc flash event inside this enclosure, it will be an explosion. The explosion will put the equipment out of service. So you always have to think about, well, what is the cost for downtime? And sometimes downtime for equipment like this could be millions of dollars per day. This Toquepala mine site, this mine is a remote application on a relatively weak system. And if the filter system were to go out of service because of an arc flash event internal, it would put the equipment out of service. And because the filter was not able to operate, the mine would not be able to operate. It would cost millions of dollars a day. So when thinking about arc flash mitigation, it's not only about personnel safety, it's also about the equipment itself. So that is the topic of today, is to speak about arc flash mitigation and hazard mitigation. So we're going to be talking about, well, what design measures can you implement when designing and specifying metal enclosed harmonic filter systems. Part of these are site specific, and part of these are designed within the equipment itself, how to specify certain parameters so that you can get a more reliable design. We're also going to be bringing up we're going to be talking about active arc flash mitigation. In particular, we're going to be talking about the ABB ultra-fast earthing switch. So we hope that you enjoy the presentation today. Remember, there's a chat box within the YouTube. Please ask questions there. And as we go forward, again, reach out to us and tell us what you want to hear, what you want to talk about, and we'll include those in future Tech Talk sessions. We're going to continue to do these on a weekly basis moving forward until we exhausted all the content that we think we can exhaust when it comes to this medium voltage metal enclosed type technology that we're supplying. So on to the presentation, and we kind of already talked about what today is going to be about. And don't forget, again, chat box and also the PDH credits. So this was a teaser video that we actually put together to get more participation for this Tech Talk session. And what this video clearly shows is that an arc flash event can be quite significant. It bends the steel, it expulses a significant amount of gas, and it takes the equipment out. In this particular case, it was an event that occurred within our equipment. It was a CPT failure, and it was quite catastrophic. So whenever thinking about arc flash mitigation, think about these types of things. Each year, there are 4,000 fatalities in the United States related to arc flash. There's 5 to 10 arc flash accidents per day in the United States, and this is significant. When an arc flash event occurs, what's going on is there's an arc through air within the enclosure, in our case within the metal enclosed capacitor bank or harmonic filter bank. That arc flash results in a significant temperature and pressure buildup within the enclosure, and that pressure buildup is significant. It can be on the order of 2,000 pounds per square foot. If you think about the square area of a door, that's over 20,000 pounds on a door itself. So under an extreme arc flash condition, it is no doubt going to cause damage within the equipment. And that is really the purpose of this presentation, is to talk about that damage. There is an economic cost. So we have a personal injury issue, and then there's an economic cost. And we've discussed this at the beginning of the presentation. This mine site purchased this filter bank. The filter bank needs to operate. Without the filter bank in operation, the mine shuts down. And that's key, is to specify equipment that will not fail. And that's what we're looking for, and that's what this presentation is about. Arc flash mitigation is about trying to prevent the failures in the first place if possible. So I start off with this very simple set of pieces of drawings that of some metal enclosed systems, and I asked the question, well, where might a fault occur within a metal enclosed capacitor bank or harmonic filter bank? And I would start to point out some things. If you just kind of think about it, you have the capacitors themselves. If the capacitors fail, it's a fault point. That is unrelated to the manufacturer, NEPSI, in other words, the metal enclosed capacitor bank supplier, the failure within that capacitor. But we as a supplier, we have the ability to choose which capacitor to use, what voltage rating of the capacitor to use, and we can apply voltage capacitors at a higher voltage rating, a higher impulse rating, and decrease their probability of failure. Capacitors themselves have a failure rate of just 1 in 5,000. So if you were to, say, bump up the voltage of that capacitor and operate it at a lower voltage, in other words, a lower stress level, its reliability would even go up higher. We often see a possibility of fuse failure. Current limiting fuses are susceptible to failure due to overload. We use a CIBA blown fuse detection system. That CIBA blown fuse detection system helps to protect the fuse from overload. Current limiting fuses, especially at the medium voltage level, are susceptible to overload and failure. What happens is the fuse heats up and the sand drops out and it flashes over within the equipment. So we use a special fuse manufactured by CIBA. It has an overload thermal element built into it that shuts the system down should the fuse go into a overload condition, thermal overload runaway. If the cables are not properly run within medium voltage systems, it's a source for flashover. You have insulator failure. You're running bus bars through enclosure walls. If it's not done properly, it can lead to failure. Up inside the resistor compartment, if the resistors connections are bad, or if some type of rattlesnake comes across the resistors, it can cause a flashover. The disconnect switch, if there's too much condensation in this compartment, we have seen that it can lead to a failure. So we install additional cross ventilation within this compartment. And then finally, the iron core reactors are another source of failure. If the reactors are underspecified, they can lead to premature failure. So properly specifying the components, properly designing the equipment can also lead to a more reliable piece of equipment, a safer piece of equipment to operate. Things such as the signage in front of the enclosure and the way it operates the protection and control system all can lead to a safer piece of equipment. So from NEPSI, we see some design strategies to reduce arc flash mitigation hazard. One of those is just to eliminate the arc flash event altogether. Design equipment that does not fail. This comes at a cost. So when you purchase capacitor banks, think about cost. Are you going to go with the low cost supplier, one that might be looking to reduce component costs, reduce voltage margins on their components, or do you go with a higher cost supplier, one that is doing testing, one that's increasing the ratings, one that is striving to reduce the possibility of equipment failure? If you can eliminate the failure within the component, within the ratings, within the system itself, you eliminate the arc flash event, and this is key. Eliminating arc flash events should be a desirable objective in any design. You also want to reduce the energy of an arc flash event. Remember, when an arc flash event occurs, you have arc through air, and it's fault current that is flowing. Fault current times time is related to how much energy is going into that arc flash event. So if we can reduce the time, of the fault, or if we can reduce the magnitude of the fault current, we can reduce the energy into default. So we oftentimes look for ways to reduce these items, and this is in the protection system that we can do that. We can supply current limiting fuses, which provide our current limiting mode and also interrupt fault currents very quickly, on the order of 4 milliseconds, so very quick. And then also think about the site conditions. What can be done on site? Okay, the energy associated with the arc flash event drops off by the inverse proportion. Inverse is by the inverse square of the distance. So putting the metal closed system out in a switchgear yard where nobody is standing and people do not hang out is a great place. Put a metal closed capacitor bank inside an e-house, inside the electrical room. That's where people like to hang out. So we always say, put the capacitor bank outside, put it out at a distance, and in so doing, you're removing the hazard from within a location where people may be hanging out and putting it outside in the switchgear yard. So this is a site type of condition. So we have many different design strategies, and we have a table, and this is a document that was produced by NEPSI. It can be found on our website. But these are design strategies that reduce the exposure to the arc flash event. And again, we mentioned where you locate the equipment is important. Delayed switching, what we do there is we install a delayed switching on our on-off auto switches. If we put the bank into manual mode, it allows the operations person to step away from the equipment and allow the system to energize while the person is standing away from the equipment. So it's a very simple, it has no cost adder. Basically, turn the stage on, walk away, it switches. When a capacitor bank switches, there's a lot of complex things going on. We're conducting current through the system. The vacuum switch is closing. We've had discussions about the complexity of capacitor bank switching transients. If the capacitor switch fails to do its job, you may have a pre-strike or a restrike condition that can result in case rupture, can result in a arc flash event inside the enclosure. So why not step away? And that's our recommendation, step away. If you have breakers within the gear, you can think about remote switching operations. If at all possible, consider remote switching. Do not stand next to the gear when you're energizing or when you're removing or recting out equipment. Remote control protection systems is something to think about. If the control and protection system is remote, then all the switching operations are in fact done at a remote location. They're not standing next to the medium voltage equipment. Arc resistant enclosure. This is something to think about, and NEPSI has developed arc resistant enclosure. The concept of an arc resistant enclosure is that we have a fault inside the enclosure, we expel the gas out the rear or out the top. We vent it away from where people may be standing. In this case, this was an arc-resistant enclosure developed for Canadian utility, and the gas would expel out the rear of the enclosure. One of the biggest downsides to arc-resistant enclosure designs is that you still have the fault inside the gear, and the gear has been potentially catastrophically destroyed. We've expelled the gas out the rear, so yes, we have saved the person, but the equipment itself has still been injured. So there are some other technologies, and we're going to be talking about that technology. One is the ABB ultra-fast earthing switch that we install in our equipment, and that actually saves the gear and also protects the person out in front of the equipment. So we also look at ways to reduce the probability of faults, and some of these are operational. Key interlock systems, for instance, they dictate a sequence of operation. They dictate when you can go into the enclosure and when you cannot. So it's an important matter. All of our banks get key interlock systems as standard. It determines when you can get in and how you switch. It determines when you throw a ground switch and when you cannot. So we do not have people making mistakes. The key interlock systems dictate the sequence of operation. We see that proper switching, proper choice of switching device as being very important. As standard, NEPSI will always up the voltage rating of their switching device. If you have a 15 kV system, we no doubt will be using a PS25, a 25 kV rated switch. Why? Because it's less likely to restrike. We have found that restriking capacitor switches is the number one cause for case rupture within capacitors. So a capacitor restrike leads to case rupture. Case rupture leads to the possibility of an arc flash event. Fuse failure, we talked about it. SIBA, blown fuse detection system. It protects against overload. There is no better fuse. If you don't know anything about the SIBA blown fuse detection system and the SIBA fuse itself, it's a German-made fuse. It's a great fuse. Go to our website. We have a technical article about this fuse and how it works. Always, we provide lightning arresters. We're protecting the equipment from lightning and switching transients, over voltage protection. It comes at no cost from NEPSI. It's included with our equipment. Windows are important. It prevents the desire to look into enclosures. If you purchase a metal closed system and it doesn't have windows, at some point along the way, some maintenance person is going to say, okay, I want to get into this enclosure. Let me see what's going on here. He will open it while it's energized to check things out. That is an arc flash hazard, and we eliminate that by putting windows in our equipment. We also incidentally put IR windows in our equipment to allow for infrared scanning. Also prevents people from wanting to open that door while it's energized. We protect against rodents. We have a significant amount of signage. If you understand the equipment, if you understand what's behind the door, you're less likely to open the door. If you have signage that tells you how to operate the equipment, what to watch out for as you step along during the operation of the equipment, you're less likely to make a mistake. It is mistakes that lead to arc flash hazards. We have a very detailed installation, commissioning, and instruction manual. You need to have details. You need to understand how the equipment works. You need to understand how to maintain the equipment. You need to understand how to operate the equipment. And these are things that should be included in every operation and maintenance manual as it applies to metal closed capacitor banks and harmonic filter banks. Glow tubes. If you think about glow tubes, it's a device that sits on a bus bar. Okay, it comes at a cost of about $600. It tells you that the bus is energized. You put it in the incoming compartment. If you open the incoming compartment door and that thing is glowing red, no doubt you will not touch the bus bar. The bus bar is telling you, hey, I'm energized. Don't touch me. We recommend a split wide current detection because we have found that neutral voltage detection that uses a PT leads to restrike conditions with the vacuum switch. It increases the transient recovery voltage associated with switching during opening, which leads to a possible restrike and pre-strike conditions in the capacitor switching device itself, which can lead to case rupture, as previously noted, and that can cause a flashover event. You can specify insulating bus bar. Okay, it's an extra measure to prevent the failure of equipment. Always think about increasing the component ratings. The cost to increase component ratings come at a fraction of the cost of the equipment. If you have a 13.8 kV system, it's rated 7.96 kV line to neutral. You don't need to pick a 7.96 kV rated capacitor. You can go to 8.32 kV, 9.54 kV. By increasing that capacitor voltage rating by 10 or 20 or 30%, you bring the failure rate from 1 in 5,000 to potentially 1 in 10,000 or 1 in 15,000. The cost difference is insignificant. Iron core reactors is another place we often see being underspecified by EPCs. They'll do a design study, they'll look at the harmonic current flow into the reactor, they'll calculate 7 amps or 10 amps on a system that might draw 1 or 200 amps fundamental, and they'll specify 10 amps of harmonic current. Our philosophy is to over-design iron core reactors. If you think about harmonic filters, there's one of the main causes of failure are the iron core reactors being underspecified. Overloading of harmonic filters is a key point of failure. So increase the rating of the iron core reactor, increase the voltage rating of the capacitor, and you will reduce your failure rate significantly in a harmonic filter. Increasing BIL is also something to think about. To go from a 95 kV BIL system on a 13.8 kV system to 110 or to 125 comes at the fraction of a cost. So again, increasing BIL means to increase the spacing. It means to increase the height of the insulators. It means to reduce the probability of a fault from occurring in the first place. So there are some active maintenance type devices you can look at. One is ultra ultrasound inspection ports, and this is to monitor for partial discharge within the equipment, corona discharge, and you can also do partial discharge monitoring devices that you can install. These things can have a significant cost, these online partial discharge monitors. Smoke detectors, if you have a fire, it's nice to detect it early and take it offline. So we're into strategies here that reduce the energy, and these are things that reduce the magnitude of the fault current. Current limiting fuses would be an example, and things that reduce the time. In particular, we have bus differential relays and arc flash detection relays. Both of these relays can interrupt faults very quickly. The arc flash detection relay that's offered by Schweitzer, for instance, the 751A, will detect a arc flash event within 2 milliseconds and send that trip signal. But that trip signal is going to a breaker, and that breaker is going to take another 3 to 5 cycles to operate. We have a very fast detection of the event, but then we have to wait for the breaker to clear the condition, and that's anywhere between 3 to 5 cycles. Bus differential relays is another great way to speed up the fast tripping within a metal closed cat bank. We're going to be talking about this ABB UFA system in just a moment, and this is a very interesting device, and this is something that really is designed to not only make it safer to operate for operational personnel, but it also provides an insurance policy for the equipment. So we won't go through all these in details, but this is just some examples of the type of technologies we use. This arc blast vent is another interesting concept. It's an arc blast vent that's got a certified blast rating to it. In this case, it's 1.5 pounds per square inch. We include these on some of our enclosures where arc flash hazard is being strongly considered. The burst vent allows for the expulsion of gases outside the enclosure should there be buildup inside, and it's a certified pressure value. I'm going to skip this video because it's about 7 minutes, and these tech talks are only about 30 to 40 minutes long. This is on our website. If you go to NEPSI.com/resources /videos, it's a review of the installation of an ABB ultrafast earthing switch within our equipment. And I highly recommend that you check it out. We show you how this operates. We show you how it is installed in our equipment, and we show how it works when there is an arc flash event. We're actually testing a piece of equipment in this project, so you can see how it actually works. And so here is another video, and this is an extract, and I will hit play on it. But this is the ultrafast earthing switch at a test laboratory. And this is something that we've taken from ABB's website. And what they've done is they shorted out bus bars within their switchgear, and they're applying an internal arcing fault. The one on the left is without the UFA system. The one on the right is with the UFA system. So as you see, this is counting the internal fault that was created with those wires. And there's a significant amount of expulsion of gases. The one on the right, you barely saw anything. So after a 50 kA 100 millisecond fault, this is the switchgear that did not contain the UFA system. You can see there's significant damage. This switchgear would need replacement. The steel is bent within the switchgear itself. You can see it received a significant amount of pressure buildup, and it would require replacement. This would be true if it were a metal closed cat bank or harmonic filter bank. If there was a fault of that level, it would create damage and would potentially require the replacement of the equipment. For a mine application or some other process, that would be a very costly item because the plant might be required to shut down. So now this video shows, well, what is the damage related to the system with the ultrafast earthing switch from ABB. You can see here they peeled back the insulation, and there is just a minimal amount of copper burning. In fact, the wire that was used to short the bus bar is still present. There is very little carbon buildup within the bus bar structure. So this literally is a dusted off, replace the failed component, and put it back into operation. So something to think about. It's very, very good system. So here's another video. This is just a 1-minute video, and it also shows how the system operates, and it's another interesting. It's another visual. And in this case, we're showing a arcing event that does not have a UFIS system. Here you can see how the system works. There's the power switching unit here. You have the bus structure here with a fault. Okay, so there's fiber optics that sense the fault and current that sense the fault. And so it's an arc detection. When the fault occurs, the PFC, the power switching units here close, which then creates a 3-phase bolted fault. In a sense, you're shorting out the arcing fault that occurred over here. And that is what you're looking for. And then you interrupt that fault with the upstream breaker. So you're shorting out the arcing fault and replacing it with a 3-phase bolted fault that eliminates the arc. And you can see from the video, basically it's gone. So it happens all within 4 milliseconds. Very, very fast. And there is a cost for this. It's not inexpensive. It's typically in the order of $25,000 to say $50,000 on a project. But if you're looking at a harmonic filter system or a metal closed cap system that's critical to the operation of your facility, and the equipment itself might even cost on the order of $1 million, then you need to think about installing this type of system, because it's there to not only protect people, but it's there to protect the equipment. And protecting the equipment is very important in process industries that require that filter to operate. The other thing to think about is testing. Okay, if you are in a position where you're specifying metal closed capacitor banks and harmonic filter banks, demand testing. Do not trust that the supplier of the equipment has built it correctly. I mean, let's face it, if you build a piece of equipment that's designed for 95 kV BIL, but you don't impulse test it, how do you really know that it's designed and built to 95 kV BIL? You're taking the word of a design engineer, that's all. So we have found that lightning impulse withstand tests and the 1-minute withstand tests are very important design verification methods to make sure that you actually get what you're asking for. It's critical to know that is being done. So I have included what I would suggest you put in your specification lines, that you have a power frequency withstand and lightning impulse. Partial discharge testing is another item that you really should be specifying, because partial discharge testing talks about or is a measure of the amount of corona that exists in the system during operation. If you have a lot of corona, what you basically have is insulation being eaten within the system, and at some point that insulation will degrade. You get tracking, and it will flash over. So being able to design equipment with a maximum amount of partial discharge at the extinction voltage is critical to determining the life of the equipment. You can easily design equipment to meet the withstand level. It's more difficult to design the equipment to meet lightning impulse withstand, and it's even more difficult to design equipment to meet partial discharge testing levels. So if you're looking to specify reliable equipment, specify these tests. It will help to guarantee that you purchased equipment that meets the standards and that has a high reliability and therefore a low likelihood of arc flash within the equipment itself. And it comes at a cost, right? Impulse test equipment has a cost related to it. We have to purchase the equipment. It's on the order of $500,000. We have to free up floor space for it. We have to have the know-how. We have to have safety procedures. And this is why most manufacturers do not have impulse test equipment at their facilities. But metal closed systems are custom in nature. Each one is custom, and therefore each one should be type tested. Just like when you buy switchgear, okay, a piece of switchgear has been type tested. Well, each and every custom metal closed cap bank and harmonic filter bank should be type tested. To say that you type tested one and then to change the design and not test the next is not proper. It should be a factory test. So this presentation is based upon these tech notes. We have them in both Spanish and in English. And if you want to learn more, go to our website and grab a copy of this technical note. There's also some videos on the UFA system I mentioned. It's very interesting to go watch that also. And the guide form specifications. All the points that we have noted in this technical article are included in our guide form specifications. So if you're interested in specifying certain aspects of arc flash mitigation, then go to this document, and there you will learn what other items you can specify. It formed an integral part of our guide form specification. So again, our website is packed with information, so go there for additional information. And here's a reminder for PDH. Use a code of 432, and we will send you some your PDH time that you have spent listening to this presentation. So inclusion, there are many ways to minimize arc flash hazards associated with metal closed cap banks and harmonic filter banks. One is create distance between the equipment and the operating personnel. Put the metal closed system outside. That's where it belongs. You want to shorten the magnitude and the duration of faults. So employ current limiting fuses as a standard when you can. Employ active arc flash mitigation especially on expensive equipment and equipment that is critical to the operation of the plant. And then finally, improve the reliability of the equipment by increasing component ratings, increasing BIL, and adding protection features to the equipment. And there are many more. And then finally, specify testing. Make sure you ask for testing.